X-ray crystallography is a technique that we can use to investigate how the atoms or molecules in a crystalline solid are ordered. So a crystalline solid, by definition, has long-range order to the atoms or molecules. There's a pattern to how they're set up. And this is how we end up with these beautiful crystal structures. This is ice, a snowflake, and you see all of this detail in here, and all of that arises from the crystal structure that ice assumes when it becomes a solid. So all of those beautiful shapes come from those atomic and molecular structural organization. So quick review about electromagnetic waves. They can interfere with each other. We can have constructive interference where the wave gets bigger. We can have destructive interference where essentially these cancel each other out. We talked about this when we talked about X-ray diffraction, electron diffraction and light diffraction, the guy with the box on the beach, right? So that's what we're talking about here. So light passing through the two slits, separated by a distance similar to the wavelength, gives us that interference pattern. Well, that was using visible light, but we can use electromagnetic radiation that's outside the visible range to investigate essentially slits or spaces that are closer together. So instead of using visible light, we can do this with X-rays. So in these crystalline solids, the atoms have about 100 picometer spacings. And so then you need to use electromagnetic radiation that has a wavelength about that long. And so that corresponds to X-rays. So we got this X-ray source, we got X-rays coming through, and we have a screen here so that we can just get a little beam of them, and it hits the crystalline solid, and it interacts with the particles in there, gets bounced around, and as those beams come back out, they're going to interfere with each other based on how they got deflected. And you get an interference pattern. So the structure, this is a ball and stick model. Obviously, the sticks aren't there. But depending on how these atoms are spaced and arranged in that crystal, you'll get different patterns here. So this is part of what's going on here. This is, some geometry, actually. And I think there might be a question on an exam asking you to use Bragg's law, but we do not need to understand how Bragg's law is defined here, or determined, or derived. That's the word I was looking for. The idea here is that we've got these two X-rays. There we go. X-ray 1 and X-ray 2. They're coming from the same source. They're in phase with each other. And they are going to bounce off of an atom. So this one bounces off here, and this one bounces off one layer below. And this is coming in at a certain angle. The angle is theta. And you can calculate how far this ray 2 went in addition to the distance that ray 1 went. Okay? Because it has to go this distance here plus that distance there, and then they come out over here. So that's the path difference. That's 2a. And what Bragg's law says is that if we have two waves coming in phase, we'll get constructive interference. We'll get constructive interference if the difference in path length here is an integral number of wavelengths. Because if this is offset by a whole wavelength or two wavelengths or 7 wavelengths, they're still going to be in phase and they're going to reinforce each other. And so we can adjust this angle and determine the distance here between the two layers. That distance is d. So Bragg's law says that n times the wavelength, n just being an integer, is equal to 2d, the distance between the layers, times the sine of theta. So typically what they do is they're going to look at the angle that produces constructive interference. And then they can calculate the distance between those layers using this rearranged form of Bragg's law. Now, that all sounds pretty straightforward, but honestly, I have never looked at X-ray crystallography data. I mean, this is an example of what was seen on an early X-ray plate. I have no idea how you take all of these smudgy spots, right, and figure out the distance between the layers. I have no idea how you do that, but it can be done. This is a technique that was really important in determining the structure of DNA. DNA has a double helix structure, and X-ray crystallography is what finally made that apparent. So let's just do a little Bragg's law calculation. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So we've got a distance, and we've got a wavelength, and this is n. So Bragg's law said that n times the wavelength is equal to 2d times the sine of the angle that the X-rays are coming at. So we're trying to find that angle. Calculate the angle. So we're trying to find theta. So we can rearrange this a little bit and have n lambda over 2d is equal to the sine of theta. We're told that n equals 1. Lambda equals 154 picometers. That's the wavelength of the X-rays. The spacing is d, and that's 157 picometers. So we can plug these numbers in. We've got 1, and we've got 154 picometers. And we're dividing that by 2 times 157 picometers. We don't need to convert any units because the units are going to cancel out as long as they're the same. So I end up with 154 divided by 2 and divided by 157. And so this is 0.49045. No units. That's equal to the sine of theta. Now, we do need to do the inverse sine. Yeah. So it's maybe been a while since you did anything with sines, cosines, tangents, those things. I didn't even especially like those. But so we've got this thing here now. So we have to get rid of sine. Sine is a function. We can't divide by it. We have to do the opposite thing. And the opposite of sine is inverse sine. So we're going to take inverse sine, which most calculators show as sine to the minus 1. That's a button of 0.49045. And that's going to give us our angle. Calculators have degrees and radians, so you want to make sure that your calculator is in degrees and not radians, or you'll get an answer in radians, and that's not what we're looking for. So and theta is equal to, we'll call it 29.4 degrees. Any questions?